Okay, so this section is about composition of functions. And we'll start off again with functions. And we define them in the last section as really just any time we have a relation, a pairing of x and y's, where there's exactly one output, one y value for any given input, any given x value. So if you put in an x value, there's only one possible y that you will get out. Another way to simply check when given a series of coordinates is that you would have no repeating x values. And on a graph, this can easily be checked with the vertical line test. Now, some operations that we have with functions is we can add them, subtract them, we can take the product or multiply, and the quotient or divide. So using the function notation, the left side is equivalent to the right side. We have f plus g of x. So that's the same as f of x plus g of x. These would be read in the same manner. It could also be, for the difference here, notated as f of x minus g of x with the x held outside, or split out like this. So the left side is the equivalent of the right side. It can be expressed in either manner. So if we take a look at a couple examples. In this case, we're given f of x equals 2x minus 1 and g of x is x squared plus 1. We need to find the sum, difference, product, and quotient of the two functions. So in the first one, in the sum, I'm going to add f of x plus g of x. And if I rewrite that below, substituting f of x for the 2x minus 1 and g of x for x squared plus 1. And this really just breaks down to combining like terms. So I have a single variable here, minus a 1 plus x squared, and plus 1. So the only things I can actually combine are the ones. Those cancel out. In this case, the sum, I'm left with x squared. It's the highest exponent, so I'll write them first, plus 2x. So that's the sum. The difference, f of x subtract g of x. I do a very similar thing. 2x minus 1, instead of writing f of x, the function notation, I'm going to write the actual expression here, 2x less 1. And then subtract. This is where you want to be cautious. Make sure you're using parentheses. And then I substitute in the x squared plus 1. So again, this has to get distributed through. So I really have a minus x squared minus 1. And again, there's no square here to take it away from, so I'll put them out front. So I have a negative x squared, a positive 2x, and I have minus 1, and then another minus 1. So that would be minus 2. So we have the sum, the difference. Now if we take the product, f of x times g of x, I'm just going to write these two binomials, 2x minus 1 times x squared plus 1. And then this is where we FOIL. So I'm going to take the first terms. So 2x times x squared is 2x cubed. Outside terms. Inside. And then last. And then we combine any like terms. I have a cube, a square, first degree, and then a constant. So I'm just going to put them in proper order. There's nothing here to combine. And then we have the quotient. And really all we need to do on the quotient is determine the domain restriction. We really don't need to go any further than that. So I have 2x less 1 over x squared plus 1. And what I'm most interested in is I look at the denominator, and I want to know what value is going to have a domain restriction. What value can x not equal? Is there one? So I know that anytime this equals 0, I'm going to have a problem. So I have a quadratic, so I'm looking to see if this is factorable. So can I factor x squared plus 1? Well, let's check. Real simple ways to use the x method or the x box method, however you were taught. I'll put the product of the first and last term in the top, middle term in the bottom, and I'm looking for things that multiply to get me the top, but add to get me the bottom. And I see that 1 times 1 is 1, but 1 plus 1 is 2. If I make 1 a negative, these will add to result in the bottom, but when I multiply them, I have a negative in the top. So actually that is not factorable. So if I check it in another manner, if I just say x squared plus 1, when will that equal 0? I subtract 1 from both sides. I have x squared equals negative 1. We square root. And what's the square root of negative 1? That's just I. So since it resulted in I is an imaginary number, and in fact what happens then is there is no real number that we could substitute in for x that's going to make this equal 0. And if you think about it, any large number, anything to the positive side, is going to then get squared and have 1 added to it, so it's never going to be 0. Any negative value is going to be squared, which is going to turn it back positive and then have 1 added to it. So you're never going to produce a 0 here with any type of real number. So for all of these, as you look through, there are no domain restrictions. So in this case, in all of these, x is all real numbers. So let's look at another example here. So I'm going to again find the sum, difference, product, and quotient of these two functions. So let's find the sum. So I have f of x plus g of x. So I have 2x minus 1 over x plus 2. I'm going to add to that 3 over x minus 3. So remember, anytime you want to add fractions, you're going to need a common denominator in order to combine them. So in this case, the easiest one would just be to take x plus 2 times x minus 3. So if I do that, I'm just going to do that over to the right here. I know that I'm going to get x squared minus 3x plus 2x minus 6. So I get x squared minus x, and this was minus 6. So there's my denominator. So I'm going to bring that over here. And then I just multiply the top of this by x minus 3 and the top of this by x plus 2. So I have 2x plus 1. Let me choose a different color here. 2x plus 1 times x minus 3. So I have 2x squared. There's first, outside, minus 6x, inside, last. Combine. So this is going to be 2x squared minus 6x plus 6. X is minus 5x minus 3. And then I multiply the 3 by the x plus 2. And that's just going to be 3x plus 6. So plus 3x plus 6. 6. So see, I have a common denominator here, so I just wrote the 2 up above. And then we combine any like terms. I have a square here, minus 5x's, plus 3x's. Then I have a plus 6 minus 3. So ultimately, this is all going to reduce down to 2x squared minus 2x plus 3 over x squared minus x minus 6. And then when we go to find the difference, well, we've already found that common denominator, so if I adjust them as such, I can work right back up into this. It's done very similarly. So this was my first, minus 3. So what I can do then, instead of adding these, is subtract. So right here, I broke apart the 2x plus 1 times x minus 3, this first part, and then the 3 times x plus 2. And this would be subtract this quantity. So that's going to distribute through. So that becomes a minus 3x. And that plus 6 will become a minus 6. And then again, we just combine the like terms. So I have 2x squared minus 5x is minus 3x is minus 8x. Minus 3 minus 6 is minus 9. That's all over x squared minus x minus 6. Now, these both have the same denominator, so we can look for any domain restrictions. All you're looking to do is to factor this out again and see what happens. Well, we know that since we multiplied the x plus 2 and the x minus 3 to produce this, that's how it would factor out. So we know that in this case, x cannot equal negative 2, because that would make this 0. And positive 3, that would set this equal to 0. So there's your domain restrictions for the sum and difference. When we take the product, clean this up a little bit. I'm going to multiply these two together. 2x minus 1 times 3 over x minus 3. And when we multiply, we go just straight across with fractions. So I have 3 times this, which is 6x, 3 times negative 1. And then I have x times x, and negative 3 times 2. And always look to factor the denominator here. We're going to set these two up. And I have 2x minus 1 over x plus 2 divided by 3 over x minus 3. Now this really starts to look complex, but remember, when you divide by fractions, all you're doing is multiplying by the reciprocal. So we're going to multiply by this one flipped. And again, we go straight across. So I have x times 2x is 2x squared. It's both binomial, so you have to FOIL this. X times negative 1 is minus x. Negative 3 times 2x. So we have minus x, and then I have minus 3 times 2x is minus 6x. Minus 3 times negative 1 plus 3. And all that's over 3x plus 6. And then we combine anything in the top here. These middle terms can be combined, so I get 2x squared minus 7x plus 3 over 3x plus 6. And then we're looking for any value down here that's going to make this error out. So I just take 3x plus 6, set it equal to 0. Divide by 3. And I know that x cannot equal negative 2. So there's your domain restriction there for the quotient. And composition of function is, or occurs, when a function is performed and a second function is performed on the result. So it's kind of sequential. You do something to one, and then you do something else to that result. So, and the domain of these, really nothing different than what we've been looking at. It's just simply composed of the domains of the functions that make up that composition of functions. So if you have the domain of function A and the domain of function B, and you have a composition of those two, then the domain is the result of the domains of the two that started or were comprising the function. You'll see what that looks like here in just a second. So if you look at this first example, I have f of x is 3x squared minus 4, and g of x is negative 2x squared, and they ask me to find the following. Now this notation here, this large circle, is not a multiplication. Sometimes it gets confused. It's f of g of x or f composition g of x. So what we're really doing is we're taking g of x and we're substituting it in for f of x. So in this case, I'm going to take g of x, which is this. I'm going to replace it into f of x, which is this. So now wherever you see x in f of x, I'm going to replace it with the function g of x. So I have 3 times, and in parentheses, I'm going to substitute the function g of x minus 4. Now a couple things I need to do here. This is in parentheses and then squared, so I do need to square this. So I have 3 times negative 2 squared is 4, and x squared is x to the 4th minus 4. This thing gets multiplied by 3. So I get 12x4 minus 4. And we look and see, is there any domain restriction here? Is there any value that I cannot sub in for x? And there is not, so I'm going to say all real numbers, or all real numbers, the R with the extra backbone. And then I do just the opposite. I take g of f of x. So now I'm going to plug f of x into g of x. So where I see x here, I'm going to replace it with that function. So I have -2 in parentheses, 3x squared minus 4 squared. So this is going to end up getting FOILed first. So I have the first terms, 3 and 3 is 9, x squared, 9x4 outside. So I have -12x squared inside, -12x squared, and then last plus 16. And all of that is going to be multiplied by -2. I'm going to go ahead and combine here first. And we'll multiply it all by -2. So I have -2 times 9x to the fourth is -18x to the fourth, and negative is positive, 48x squared. (48x squared). -2 times positive 1 is -2. So there's my function there, g of f of x. And again, I'm looking for any domain restrictions. There don't appear to be any. So again, all real numbers. That just says that there's no number that's real that I cannot put in for x that I will not get an output value for. And you can check that on your graph too. You'll see this creates a function that extends indefinitely both directions and does not have any asymptotes. And in this last example, finding the composition of f of g of x, again, we're going to go ahead and in this first one, f of g of x, take g of x and swap it in to x in the function f of x. So we'll rewrite it here. So I have 1 over, and I have 6 over x minus 2 plus 3. So in order to begin to solve this, then I'm going to need a common denominator to combine the 6 over x minus 2 plus the 3. Now this is just 3 over 1, so I'm going to make that denominator x minus 2. To do that, I multiply top and bottom of this 3 over 1 by x minus 2. So this is going to become (3x minus 6). I can now combine these two because they're over the same denominator, and that's just going to be 1 on the numerator. Then I have 6 plus 3x minus 6, that's just 3x over x minus 2. So now I have 1 divided by this quantity. So instead of dividing by a fraction, I'm going to multiply by the reciprocal. And then when I write this out, I have x minus 2 over 3x. So here's my solution then, x minus 2 over 3x. And I look for domain restrictions. When will 3x equal 0? Whenever x equals 0. So I know that my restriction, x cannot equal 0. So I could say all real numbers except x cannot equal 0. And we do the same thing here with g of f of x. And so now I'm going to take f of x and swap it into g of x for that x value. So I have 6 over 1 over x plus 3 minus 2. And we do the same thing here. I'm going to multiply top and bottom here by x plus 3 to make that my common denominator. And then this, 2 times that will be 2x plus 6. So then I combine these two, and I have 1 minus 2x plus 6. So I actually have a negative 2x, and then 1 minus 6 becomes that. I flip this to multiply by the reciprocal. And go straight across with it. So I have 6x plus 18 over negative 2x minus 5. Again, I look for the domain restriction. So I have negative 2x minus 5. When will that equal 0? Divide by the negative 2. And all real numbers, except x cannot equal negative 5/2. So bring your completed notes to class tomorrow, and we'll begin practice on the assignment.